All right, what I want to look at today, we're starting chapter 8. We're starting chapter 8, which is going to deal ultimately with similarity. Okay, now what's that mean? We've talked about it a little bit, but not much. Let's put it in context with stuff we've already talked about. Remind me real quick, what is congruency? If I say that two things, Travis, are congruent.
I'm trying to learn.
You're slowing us down. We're going to be in the lab 2 days now, probably. I mean, if we keep this up, we're going to be in here 2 days. I would do this one, but I'm not even going to try if we can't kind of come together and get this done. Okay, what does it mean to be congruent?
Same size, same shape.
Same size, same shape. Very good. Okay, now what if we relax one of those two criteria and say, okay, we want it to be the same shape, but we don't care about the same size. Then we get kind of scaled up or scaled down versions of things, right? Scale models, sort of. That's what we mean when we talk about similarity. Shapes or figures or whatever, geometric things are similar if they're the same size but not the same shape. In order to talk about similarity, though, we need to be able to quantify that difference. If they're not the same size, we need to be able to describe accurately, well, how are they different? How many times bigger is one than the other, or vice versa? And so, to get at that, we need to be able to use ratios and proportions, and so we're going to lead off by just doing a little review and coverage of ratio and proportion, and then that's kind of what the first two sections deal with primarily, and then we'll start to get into the similarity stuff in more detail after that. So we're going to focus on this. Now, it's not new. Nothing we do is going to be absolutely new, but parts of it will be. So, okay, first of all, what do we mean when we talk about ratios? A ratio is a fraction, right? Ratio means fraction. So if we have these two quantities, A and B, then we could write the ratio of A to B as the fraction, A divided by B. That's probably the best way. Or we could also write it this way, with a colon between the two quantities. And that also means a ratio, okay? So for example, if we take the ratio 6 to 8, that's the same as the fraction 6/8, which reduces, right, to what? 3/4. So that ratio would reduce to 3/4, or 3 to 4. Okay? All right, now, when we're dealing with ratios, sometimes we're dealing with actual quantities, measurable quantities, like distances. So what do we do? Let's take this first example here, example A. Yeah, I'm gonna pause and wait for a few people over first. Hang on. Okay, this first one. What do we do with this? Now, what's the answer? 3. Yeah, it's 3. 3/1, which is the same thing as the number 3. The rate 3 to 1 is the same as 3. Now, what about the units? Yeah, they're both centimeters. Units you can treat like variables. If you divide like variables, like for example, I'm going to wait again. I've still got some people that aren't 100% with me. I'm sorry that the whole class has to wait for this, but that's the way it is. Okay, does everybody think we're okay to keep going here?
Yeah.
All right. So, if we have like units like this, we treat those like variables, and they cancel. And so I just end up with the number 12/4, which is a ratio that reduces easily. Same thing here, right? Feet over feet, the feet cancel. And we end up with a unitless quantity. We just get 6/18, which reduces to 1/3. Okay, now what does that mean? In this first ratio, explain to me what that ratio of 3/1 or 3 to 1 means. Okay, 3 times more in the top, right? The ratio of the top to the bottom is a 3 to 1 ratio. 3 of the top for every 1 of the bottom in the first example. In the second example, it's reversed. 1 of the top for every 3 of the bottom, right? So that number is meaningful to us. That 1/3 is telling us, we get 1 to 3 of whatever we're measuring. Okay? What about the last one? Inches cancel, and I get 1 over 2. Okay. Very good. Okay. Now,
You just leave that as a one.
okay, you see the difference? Yeah, it looks like 3 over 1, right?
Yeah, but it's 3.
But it's not. Now think about that. 12 centimeters to 4 meters. Is 12 centimeters 3 times bigger than 4 meters? No, it's not. 12 centimeters is tiny compared to 4 meters. So the top, in reality, the top is much smaller than the bottom because the units aren't the same. We're not comparing apples to apples here, right? So we can't cancel the units. Until we can cancel the units, we can't get a number out of this. So what do we have to do? Okay, we gotta move the decimal, sure, but I want to be a little more careful with that. I mean, it's eventually maybe you can just do that little trick, but
Wouldn't it be 12 over 400 then?
okay, good. So we've got to change. We got to do a unit changer here. We got to convert one of these units into the other one before we can cancel. Good. Now, what's easier to do? And Travis essentially already gave us a good answer here and answered this question, but we got 2 choices. We would either convert 12 centimeters into meters or convert 4 meters into centimeters. Now, Travis chose converting 4 meters into centimeters, which I would agree is the easiest one. Why?
Because it'd be 0.12.
Okay, good. Otherwise, we'd have to use a decimal. We can avoid having to use a decimal if we convert the big unit into many of the smaller units, right? Okay, good. So what does that look like then? Now, this is something you're going to do a lot in math and science. We want to do unit conversions. Here is the best way to do it. You're always going to multiply by a changer. Now, when you set up the changer, here's how you do it. You start with the units. If we're trying to convert meters into centimeters, then we want to be able to cancel the meters and get centimeters instead, right? So then the unit that we're trying to cancel, meters in this case, if it's on the bottom to start with, in our changer, where does it have to show up? On the top, if we want to cancel it, right? So we need to get meters up here, which leaves centimeters on the bottom, right? Because we want those meters to cancel, okay? Now, when we write a changer, we want to write 2 quantities that are the same. The fraction has to be the same on the top and the bottom. Well, the easiest quantity in meters and centimeters that we can write that's the same for both would be 1 meter, right? 1 meter is how many centimeters? 100. Okay, good. So then the meters cancel, and if I multiply straight across, I get 12 times 1 is 12 centimeters over 4 times 100 is 400 centimeters. And now the centimeters cancel, right? Yes, sir.
Couldn't we just convert it if we just do it in our head?
Well, you can, but that's a place, I mean, eventually, yeah, you can. That's fine. Once you get really familiar with this, but sometimes that's harder to do than others. Like, what if these weren't, for example, centimeters and meters? What if they were yards and inches or something? And then that conversion is not so easy to do in your head because it's not just moving a decimal, right? So I want you to know how to do this. Okay, so now the centimeters cancel, and I could reduce that fraction. What's the easiest or the biggest number that divides into both the top and the bottom? 2 does, yeah. Is there another one? 4 does, doesn't it? Yeah, 4 does. 4 goes into the top how many times?
3.
Into the bottom? 100. Good. And we could have even cross-canceled back here a little bit, couldn't we? We could have said something like 12 over 4. Once we get the units canceled, we get the units all the same. We could have even cross-canceled and made that 3 over 1. Right? Okay. Make sense? And we could have even, if we wanted to, canceled those centimeters right there, couldn't we? Right? Either way, though, we get, that's our ratio. Okay, we had to convert the units first, and then we get a number. We got to get the units to cancel. Okay. So what about something like that? Same deal, right? I would have to just probably convert feet into inches, right? And then I could get these things to cancel. Okay, not a big deal though. All right, what about something like this? Now here's the next issue. This is a biggie. It's not hard, but it's really important. The perimeter of a rectangle is given as being 60 centimeters. Okay. The ratio of side AB to side BC is 3:2. Now, what does that mean? Describe that. Okay, good. Well, not 3 times bigger. It's for every 3, whatever we're measuring this in terms of, 3 inches or 3 centimeters or 3 miles or whatever we're talking about, for every 3 units of distance in AB, side AB, we get 2 in BC, right? Does that make sense? So this one's going to be a little bigger than this one is, always in the same proportion. Agreed? Okay. So how many different possible side lengths could you come up with that would fit that ratio? Let's not worry about the perimeter for now. Let's just worry about this ratio.
6 over 4.
Okay, 6 over 4 would work, wouldn't it? We could say that AB is 6 and BC is 4, and that would work, wouldn't it? We could make it 3 and 2 if we wanted. What's another one?
12 and 6.
Not 12 and 6. 12 and 8 would work, right? That would be a ratio of 3:2. How many, if we sat here and just talked about this, we could keep going, how many could we come up with? In fact, an infinite number, right? They wouldn't all have to be nice integers either. We could come up with decimals and square roots and all kinds of stuff if we wanted to. There are infinite number of possibilities, but if we also add in this other piece of information, we might call a constraint in math, that the perimeter has to be 60, how many of those possibilities that we could come up with do you suppose would also work for that perimeter?
Infinite? About 15.
Like 1. Right? There's only going to be one combination where we get the right ratio of side lengths that also produce a perimeter of 60. Okay, now this is where the problem-solving part of math comes in. This is what math is really, I think it's really for. Even if you don't end up doing math, everybody that's going to do anything of any significance in life is going to have to do some problem solving, some analytical stuff. You have to analyze something and figure out a way to solve the problem. How do we solve this problem? I mean, there's a bunch of approaches we can take. Some are definitely much better than others. How are we going to find the right combination of side lengths that adds up to a perimeter of 60?
X plus X equals 16.
What's it going to be?
X plus X equals 16.
Well, you're on the, I like the idea, but I don't agree completely. I like the idea of getting some X's in there. Okay, well that's what we want to, we need to make, this is not, I want you to not think about this in terms of just being able to solve a problem. That's not the issue. This is just one problem. There's a ton of different kinds of problems we can come up with. What I want you to take away from this is, what's the process? What's the analytical process we could use? It's going to involve some mathematics, some algebra. But what's the process we could use here to solve a problem like this in general? So you got to really focus. You got to turn on that thinking cap and really engage yourself, and you'll get it.
3 over 2X equals 16.
Okay, now we're on to something. There's one possibility. People didn't throw it out, but one thing that you might do is you might just say, well, let's just try numbers, right? And that's human nature would be almost to try that first, because that seems like the path of least resistance. But is that really a productive way to approach a problem like this?
No.
Not really, is it?
You can kind of find an in-between inside the tables.
You might, I mean, if it works out to be nice integers, yeah, you probably could get the answer that way. But in reality, if you were doing this problem on a job, or a related problem on a job, it's a real-life problem, what are honestly the odds that the answer is going to come out to be something nice and neat like integers? You know, I mean, like 1 in a billion. It's not going to be that way. More than likely, it's going to end up being some weird answer that you've got to arrive at in a different way then. You can't just guess and check. That's not productive. It's not efficient. That's what algebra does for us. Is algebra sets up a way where we can narrow in on the one exact answer efficiently. Okay, now, how do we do that? If we know the ratio of the two sides is 3 to 2, but we don't know what the lengths are. If so, we threw some possibilities out, like we threw out, for example, we threw out 12 and 8. If this side is 12 and this side is 8, well, isn't 12 really just 3 times 4? And 8 is 2 times 4. So I took this original ratio and I extended it by a factor of 4 to fit the perimeter, right? If I chose, instead of 12 and 8, if I chose 30 and 20, I just extended both sides by a factor of 10 in that ratio. But they still fit the ratio, right? Okay? We don't know how much to extend each side to fit the perimeter exactly, do we? So why don't we call that, that's not known to us, that's an unknown. Why don't we call that x? That's when we have an unknown, we assign it a variable. So instead of trying to pick an exact number, let's just say this. Let's just say that this side is going to be 3 times something, and this side is going to be 2 times the same thing. We'll figure out what that something is, right? If we can set up an algebra equation. Now, when you're doing algebra, the danger in algebra is if you let it get too algebra-ish. If it gets too abstract, and you get worried about the rules of algebra too much, you kind of lose sight of what you're doing. You guys are good at algebra. You really are. I mean, you are so much further along in your algebra ability than students have been in the past that I've seen here in Pendleton. It's not even funny. You have really a huge leg up on where people used to be. Partly because we do so much algebra and geometry now. So you're fine with that. Your intuition and your insights and you know what to do. Now just think about how I can set something up to use that algebra on. Worry about the application instead. We know in algebra that if I have a single unknown like this, I'm trying to solve for it. If I knew x, I would know how much to extend each of these two sides to get the right perimeter. I got to solve for x. How many equations do I have to come up with involving x to be able to solve for it? One is all I need. I only need as many equations as I have different variables. I only have one variable, x. So I just need a single equation involving x. And I can use all that algebra that you're so good at to solve for x by isolating it. Once we get the equation, we can just kind of forget about the problem and just shift gears into math mode and do the math, right? Now, what's that going to be? Okay, there it is. We know that the whole perimeter is just going to be 3x plus 2x plus 3x plus 2x, right? And all that has to add up to what?
60.
There you go. So that's our formula, right? So we end up with the formula 2 times 3x plus 2 times 2x.
Hey, can't you do that distributed property?
Yeah, now that's pretty easy. You guys can all do that. That is not a hard algebra problem. I know everybody in here can do that problem. So let's grab this guy. How about?
Run to the bathroom.
Sure.
Power walk.
Sure.
Okay, so how do we go about solving this? Real quick, this piece of cake, how do we do this? 2 times 3x is how many x's?
6 plus 4x equals 60.
So how many x's?
10x.
X equals 6. So if we go back then to our drawing here, that 6 is the number we're going to extend each side by, right? So this is actually, instead of 3x, that's actually the number 18, and that's the number 12. There you go, right? How about that? Not that big a deal, right? Okay. Oops, went one too far. Okay, what about this one? Same kind of deal. Same kind of deal here. This time we're told that the measures of the angles in triangle JKL, so that's angle J, angle K, angle L, right, are in the extended ratio 1 to 2 to 3. Now, what in the world is that supposed to mean?
In every
3 angles. And what does this mean, though, when I include this 1 to 2 to 3? That's a lot of information in one little... Okay, for example, tell me, what's the ratio of the measure of angle J to the measure of angle K? 1 to 2. Good, right? J to K goes 1 to 2. What's the ratio of the measure of angle J to the measure of angle L? 1 to 3. Good. What's the ratio of the measure of angle K to the measure of angle L? 2 to 3. So we get all that information included in that one extended ratio. That's the one time that I would argue that the colon formulation or expression of a ratio is better than a fraction, is when you want to do an extended ratio like that, because it gives you all that information in one little item, tells you a lot. Okay, so then find the measures of the angles in this triangle. Once again, there are an infinite number of possible combinations that have the extended ratio 1 to 2 to 3. For example, 1, 2, and 3, or 2, 4, and 6, or 10, 20, and 30, right? Agreed? Okay, but we need to find how far are we going to extend this ratio to fit our situation? What's the number x we're going to multiply each of these angles by so that they keep that ratio but have the right sizes? Okay, yeah, what's our equation going to be? What's the piece of information that we need to know about a triangle here? They add to 180. Very good. So then I'll say this is 1x, this is 2x, and that's 3x that are in that ratio of 1 to 2 to 3. Yeah. And we just go add them all up. 1x plus 2x plus 3x is 6x equals 180, so x is 30, right? So then if I go back to that picture, x would be 30, 2x would be 60, 3x would be 90. It's a 30, 60, 90 triangle, right? Okay, make sense? All right. All right, we're rolling. This is good. Oh, I want to skip through this one. Okay, another type of situation that we'll need to be able to deal with here is something like this. Okay, now what about this case where we're given, I think I went too far. Okay, ratios of side lengths in this case are, of these two triangles, DEF and ABC, are 2 to 1. Right, so that's telling us that's how we're scaling this thing up. This one has been shrunk, so this is half as big as this one, right? Okay. Now, how are we going to find the unknown lengths?
You divide the bigger triangles twice the size of the small.
Yeah. So what's that one got to be? It's got to be 4, because the ratio 8 to 4 has to be 2 to 1, right? What's this one have to be? 6, okay. 6 to 3. Yeah, and then we can find the hypotenuse of one of these. And then we need to know, if we know one, we can use this ratio. Now, what this is a builder's triangle. What's the hypotenuse going to be of this small triangle? No. Okay. Say it again. 10 and 5. Yeah, this is going to be 5, isn't it? Because 3 squared plus 4 squared, that's 9 plus 16 is 25. So this side must be the square root of 5, which is the hypotenuse, which is 5. That's a builder's triangle. We say, I think I told you about this earlier, because it's a really easy right triangle. If you want to get to use when you're measuring stuff, if you want to get a perfect square joint when you're building something, then you just measure, you measure up from the corner 3 feet or 3 meters or whatever in one direction, 4 feet in the other direction, and then you can just bend this thing until when you stretch a tape measure across there to those two places, it's got to be exactly 5. And when it's exactly 5, then you nail it in place, because that's a perfect right angle. Okay, so if that's 5, you told me that's 10. Perfect. Okay? All right, so shifting gears. We want to look at some properties of proportions, some algebra stuff. This is, you already know most of this though. Using proportions, well, I don't think this is a big deal, but we know that if we set up a ratio equation like this, a proportion, then we could say that the numerator of the first ratio and the denominator of the second ratio, together we call those the extremes of the proportion. The denominator of the first and the numerator of the second, we call the means of the proportion. Not a big deal. There's one situation where we're going to need to maybe draw on that a little bit, but not very much. More than that, we just want to be able to solve ratio equations. So there's two things we can do that are very handy. This is the winner by far. The most common thing we do is if we've got a ratio equation like this and we want to solve for a variable, we'll look at an example or two in a second, we can always get rid of the fractions by just cross-multiplying, right? And then we end up with no more ratios. So A over B equals C over D. If that's where we're starting, then I know that the diagonal A times D must equal the diagonal B times C. Okay? We also know that we can just flip both sides of the equation if we want to. And it still stays an equation. Now here's where this stuff comes into play. What if we've got something like this? Okay, how do we solve this for x? No. Okay, we could flip both sides, but just as a general rule, the easiest thing is just cross-multiply. Just cross-multiply. If I do that, so if I'm going to get that diagonal, x times 5 is just 5x equals this diagonal, 4 times 7 is 28. Now what do I do to get the x by itself? Yeah, divide by 5 and I get 28/5, right? No biggie. Okay? What about one like that? That looks a little uglier. 3y. Same deal. I'm just going to cross multiply. So if I do this diagonal, 3 times y is 3y. If I do this diagonal, now that's the one I got a question for you on. How do I do that? How do I multiply y plus 2 times 2? Okay. I'm doing 2 times y plus 2. But when I'm multiplying by something that's got multiple terms, it's a quantity. I got to put it in parentheses, right? So then that's right. That's just going to end up being, if I distribute 2y plus 4, right? And now how would I solve that equation? Subtract 2y. So I get y equals 4. How about that? Okay, good. Good. All right. Let's see. Yeah. Okay, so let's keep going with that. Okay, we did this stuff already. We'll skip that. Okay, what about this? How could we set up a proportion here? If we know that we're given that the length of AB divided by the length of BD, so there's AB, there's BD, is equal to the ratio of the length of AC divided by the length of CE. Okay, how could I solve for the length of BD, which we're calling x? So solve for x. Okay, so what can I do with this?
16 over x.
If I plug stuff in, what does that ratio become?
16 over x.
Okay, 16 is AB, right? So 16 over x equals, what's the length of CE?
10.
10. Okay, yeah, the length of AC is going to be what?
30 minus 10.
30 minus 10. If the whole thing, if AE is 30, CE is 10. There we go. That's no big deal. Right? Good, good. Okay, so if we're going to solve this for x, why not, before we cross multiply, why not see if we can reduce either of those ratios? Well, 20 over 10 reduces. Now, there's a great trick for this. I can just divide both sides, or top and bottom, sorry, not both sides. I can divide top and bottom by 10 by simply canceling a 0, right? So that's just 2 over 1. And now when I cross multiply, I get 2x equals 16. So what's x? 8. Very good. 8. Okay? Okay, so here's something a little bit new. You probably haven't seen this. The geometric mean. Now, when we talk about averages, there are different kinds of averages we can refer to. If I asked you, let's say that somebody's got $20 and somebody else has $100, what's the average amount that they have? How would I figure it out? Add them and divide by 2, right? 20 plus 80 is, did I say 20 and 100? Oh, 100. Okay, so 20 plus 100 is 120, divided by 2 is 60. That makes sense because $60 is in the middle. That's exactly halfway in between 20 and 100, right? 60 is 40 more than 20 and 40 less than 100. Agreed? That's one kind of average. That makes sense. There's a different kind of average, though. There's something called the geometric mean that also makes sense. Sometimes if quantities are changing, but they're not changing linearly, if they're changing geometrically, we'll talk more about this in the future, but if quantities are increasing the rate at which they're growing, and I want to know, for example, let's say I want to know a town starts out with a population of 5,000 and it grows geometrically, so every 2 years it doubles its population or something like that, let's say. Then, yeah, that's going to give us a different kind of answer. Now, let's say it ends up with a population down the road of 1 million after a long time. We want to know, when did it do half of its growth?
500.
Okay, yeah, that's maybe not where. 500,000, it would have grown like this, and so it would have hit 500,000 very near the end. To find out when was the midway point, at what time had half of the growth happened, we'd have to think about this problem a little differently. We have to find a different kind of average. Well, this is that kind of thinking, that a geometric mean deals with that kind of thinking. For stuff that's growing not arithmetically, but that's not normal linear growth, it's going to grow geometrically, and we want to find an average, we do it differently. We set it up this way. If I write two ratios, a over x equals x over b, then if we can find a number between a and b so that the denominator of the first fraction and the numerator of the second fraction are that number, call it x, and those two ratios are equal, that's what we call a geometric mean. Okay? That number is always going to exist, it's just a matter of finding it. Okay, so if we wanted to find that, the math isn't hard. If I wanted to solve for x here and I cross multiplied, wouldn't I just get x squared equals a times b? How do I solve for x? Square root. So the geometric mean would just be the square root of a times b. So if I ever want to find the geometric mean of two numbers, that's all I do. Take the square root of their product. So for example, what if we wanted to find the geometric mean of 20 and 100, like we did before? The geometric mean of 20 and 100 would just be the square root of 20 times 100, which is just 2,000. Square root of 2,000. Anybody have a calculator real handy here?
Yeah, you
Put
could.
40 zeros on that.
Oh, whoops, did I? Oh, I did. You're right. 20 times 100 is 2,000. Square root of 2,000 is what? About 141.2, something like that? Oh, hang on, that's not quite right.
141.44.2.
I messed that up. Hang on. 2 times 2,000, square root of 2,000.
You want to see it calculated? I have it.
What did I do? 20 and 100.
So should that be like 40 or something?
No, should be 70.1,
Mine's
I think.
141.42.
What did I do wrong here? Whoops. No, I get 40. I had that wrong. I get 40. I had that totally backwards. I get 44.72. Okay. So X is roughly equal to 44.7. Okay. Now, why is that? That's not before we got 60, right? But if this thing is growing, if it's picking up the rate at which it's growing, then it's going to start off by growing slower and end up by growing faster. If it were growing through time at this rate, then wouldn't it take longer to get to from 20 to about 45 than it would to get from 45 to 100, because it's growing faster at the end, right? So assuming that we're measuring time, this is how far we'd want to move along from 20 to 100 before half the time would have elapsed. Right? That's a geometric mean, okay? We'll see some applications of that soon, but it's easy to calculate. So if we wanted to do that, now here's an example. We know that 8 over 12 equals 12 over 18, so 12 would be the geometric mean of 8 and 18. Okay? Okay, we could do another example. We know, for example, here, are we going to have time? Nah, we're done. We're out of time. Are we out of here at 45? Yeah. Okay, we just about got it. So